How's everybody? Good. I'll just judge by the 3 responses that I got. A thumbs up, a good, and a, what did you say, swell? Pretty? Oh, swell. We'll go by that. Everyone else must be great. I'm just kidding, we're live. What was that? Right. Huh. Is the football game tomorrow at home? Yeah. Oh gosh, I was thinking it was Friday. Well, we never have class on Friday. I'm that anxious for the weekend already. All right. Well, we have had some games on Friday, so that makes sense. Yeah. Anyone going to the game? All right. Cheer loud for us. So there's a couple problems up there to work on, and I heard that some of you really enjoyed the puzzle we used last time. It was actually connected to what we were learning. This one is not, but I threw up a fun puzzle there if you finish the other ones, or if you are just lazy and don't want to work on the other ones, or if sometime during the lecture you're bored, you can think about that one. All right, let's get started with a prayer. Any volunteers to offer a prayer for us? Thanks. The people online already thought we were saying a prayer because they can't hear the prayers anyway. So go ahead.
Dearly Father, thank you for this day. Thank you for this opportunity to be here on campus. Thank you for this lesson that the Lord has prepared for us. Please bless that spirit of learning may be with us today, that we may learn these concepts and learn how to apply them into our homework and to everything we need to. And please bless all those that can't be here today because of COVID or in quarantine, that a spirit of healing can be with them as well, that they may be back here as soon as they can. And to say these things in the name of Jesus Christ, amen.
Amen. Thank you. Okay, let's go ahead, take a couple minutes to work on these. A couple minutes, I'll start doing a problem up on the board, that first problem. I'll probably do mine a little bit differently than you, but that's okay. Lots of different ways to do that first one. All right. So I just finished mine. It's like the third time I've done this problem today, so like I could go pretty fast on mine. So one of the reasons I did mine probably looks different than yours, and I did mine different to emphasize a point that if we only care about finding the determinants and not care about finding solutions to a system, but we only care about finding a determinant of the matrix, then we can do row operations or column operations. And we make the same adjustments for row operations that we do for column operations. If I swap two columns, it changes the sign of the determinant. If I change two rows, it changes the sign of the determinant. If I multiply one column by a non-constant scalar, then it changes it by that constant. So you can do rows or columns. So I chose to do a column because I liked this one here and this 0 here. If I could get them right here, that was going to save me some work. So just using a bit of strategy there. So I swapped those two, and I get this 1, 0, 1. But since I swapped two rows, I pulled out a -1 here. Then I used this one, multiplied this first row by a -1 and added to this row. And to make this 0, and I get two -5s down here. So then I'd like to make this a 1, so I multiplied by a third. So there's two ways to think about this. I can think of, I multiplied it by a third, so now the determinant of this is 1/3 as much as it was. So I have to multiply by 3 to keep it equal. Does that make sense? It's one way to think about it. Or you may have noticed on the notes from the video, I walked through on the video before class, someone had written on there, I pull out a 3. So you can think about pulling the 3 out of this row also. So to keep it the same. So whether you think about putting the 3 here to compensate for multiplying by a third, or think of pulling out the 3, either way you get the same thing. But it's two different ways to think about it. And then use this one here to get this -5 to be 0, so multiply by this row by 5 and add, and this one it becomes 0. At this point, I end up with a -5 plus 5/3, and that's the same as a -15/3 plus 5/3, so I end up with a -10/3. So, and now this is nice. This is really nice. Why? Because it's a triangular matrix. And I can evaluate the determinant just by multiplying down the diagonal. So I get a -10/3 times a -3, which gives me just 10. Which some of you may have recognized, this is the same problem we started on yesterday, and the determinant was 10. So you may have done different row or column operations, but you still should have got the 10. So, any questions? Yes?
So when, I remember like there's somewhere in the book when we figured out a constant that we had to raise by the power of n. So it's not in this page.
Ooh, yeah. So my question is, when do you, there's something in the book about raising to the power of n, that k times the n. If you multiply one row, so Ka, Kb, Kc, De, F, G, Hi, then the determinant of this is just K times that ABC, that alphabet matrix. Okay? Because here we just have one row. If we multiplied the whole matrix by K, then we multiplied K by this row, and by this row, and by this row. So I had to multiply K out 3 times. And so you get K cubed times this. So yeah, so great distinction. Glad you brought that up. So yeah, if the whole matrix is, if you factor out the whole K from the whole matrix, then that changes the determinant by K cubed. You've changed it that much. Or Kn. If it's a 4 by 4, it's K to the 4th. 5 by 5, K to the 5th. But if it's just one row, then it's just by K. Good. Okay. Other questions? Porter.
Question on Zoom of how come we can just use row or column operations to find the
So how come you can use either?
Yeah.
How come you can use either? We will prove, well, I've got the proof up there on the board, but the determinant of the transpose of a matrix is the same as the determinant of the matrix. And so the row columns and the column operations are just row operations, but on a transpose. So that'd probably be the best reason I could explain. Row operations don't change the solution. Column operations will change the solution, but they don't actually change the way they change the determinant is the same as the row operations do. So you can't do column operations when you're looking for solutions in the same way that you do row operations. But you can do them if you just care about finding the determinant. Okay. All right. Thank you, person on Zoom. And thank you, Porter. Other questions or comments? Molly? Oh, so I multiplied this row. Let me change colors here. I multiplied this row by 5 and then added it to this row. Yes. Yeah. So that last one was, yeah, row 3 plus 5 times row 2. Exactly right. Thanks. Okay. Other questions, comments? Okay. What's the determinant of the inverse of the following matrix? The determinant of that matrix we already did last time, it's 15. What's the determinant of the inverse of the following matrix? It's 1 over 15. So this is the argument I give for this is if you think about transformations, matrices as transformations that will change the area or a volume constructed by the vectors, then if the transformation takes a unit, takes something that's 1 square unit or cubic unit or unit to the nth power. If it changes it by, if it increases it by a factor of 15, well, the inverse to undo that better shrink it by a factor of 15. So the inverse better be 1/15. The determinant better be 1/15. Okay, so helping to think about being able to think about transformations and the connection with the determinants have to the areas and volumes and hypervolumes can help you reason why these would be true. Okay, what's the inverse of the transpose of this matrix? It's the same, it's 15. Okay, I already, to answer that one question, I already looked ahead, explained the determinant of A is the same as the determinant of A transpose. We'll walk through this proof later. Yes? Oh, yes, it did mean that. It sure did. That was kind of silly. Who wrote that thing? No one called me out on that the first class. Wow. What is the determinant? Okay, you can think about that fun puzzle while I finish this. Okay, I'm done. So, yeah, what's the determinant of the transpose of that matrix? Sorry. Yeah. We'll find other mistakes on other slides, but those I actually pulled off the internet. So I'm blaming whoever put them on their website. I caught a couple when I quickly went through, but I missed some. Okay. At the end, maybe we'll talk about that problem. Well, does anyone have any clarification questions about the puzzle? I don't want the answer. Okay. Yes.
So south, north, and east are directions, right?
Yep. Like the compass directions. So if you're, yeah, it's not the South Pole. That's exactly right. You can't walk south from the South Pole. Any step you take from the South Pole is going north, which sounds like an answer to some other puzzle, like where on the Earth, where are 2 places on the Earth that no matter which direction you go, you're going the same direction? The North Pole and the South Pole. So directions used in 2 different ways that way. No matter which way you face at the North Pole and take a step, you're going south. No matter which way you face the South Pole and take a step, you go north. No, that's not part of solving this puzzle. So, but when I give this puzzle, the first thing is someone who says the South Pole, and I'm like, no, you can't go south from the South Pole. So, okay. So these should all be reviewed, but I just want to go back and remind ourselves about properties of determinants. Some of these we'll talk a little bit about to understand why. And the last one is this determinant of A equals determinant of A transpose. We're going to walk through a proof of that. So the Laplace expansion theorem, it says the determinant expanded across any row or column will give you the same determinant. So you can choose any row or column to do the cofactor expansion on, and you will get the same value at the end. So that's the Laplace expansion theorem. The book spent like 2.5 pages trying to prove that. So, I mean, it did prove it. So you don't have to know that proof. If all the elements of a row or column are zeros, then the value of the determinant is 0. Well, we know that the determinant of A is 0 if and only if the matrix is non-invertible. So, we already know that if you've got a row of zeros, you have a matrix that's not invertible, so the determinant better be 0. So, the determinant of the identity matrix is 1. It's a triangular matrix. You can multiply down the diagonal. So the 3 row or column operation ones, if B is obtained by adding C times a row of A to a different row, then the determinant stays the same. It stays the same. We can use this example over here. Here I've added 5 times the second row and added it to the first row. And the determinant of that is still 1 because it's still a triangular matrix. So if you start with the identity matrix, no matter what you do, you can take any row, multiply it by any non-zero constant, add it to another row. you'll still end up with a triangular matrix, and all of your diagonals are still 1. So you don't change anything. So row and column operation 2. If any 2 rows or 2 columns of a determinant are interchanged, the value of the determinant is multiplied by, well, that looks bad. It looks like it by 1, but that's negatives hanging out over there. There, is that better? Okay. We've already used that one today. Row and column operation, if all elements of a row or column of a determinant are multiplied by some scalar number k, and the value of the new determinant is k times that of the given determinant. We already used that one today. And then this is the point that you brought up. What's your name? Isaac. That Isaac brought up. Yeah, A be an n-row square matrix and k be any scalar, then k times the whole matrix. This isn't just a row. K times the whole entire matrix will change the determinant by k to the nth power. So you're just applying the row operation n times to factor that out of the whole matrix. Any questions on this? Ian, yes. So, yeah, so dividing by 3 did make it so this determinant is now a third of what this was. So I have to multiply by 3 to get it to keep it equal. So that's right. Good job. Other questions or comments about any of these? I know this is boring stuff. Okay. Boring doesn't mean not important, though. If 2 rows or columns of a determinant are identical, or one is a linear combination of the others, the value of the determinant is 0. Because we know that if any 2 rows or columns, it says determinant, that should say matrix. Well, yeah, determinant of a matrix. If 2 rows or columns of a matrix are identical, or if one's a linear combination, then you know it's a non-invertible matrix, right? And we know the determinant will be 0. The product property. So this is one that I haven't given a great argument for yet. So this will be my attempt. So this says if you take the determinant of a product of matrices, then the determinant of that is the same as just taking the determinant of each matrix and multiply them together. So if you think about a matrix again as transformations that change areas and volumes, then, and you have 2 matrices and one doubles the area or volume in its transformation, and the next one triples the area or volume of that transformation. If you apply both of those transformations, you will 6 times the area or volume of your original. So you should get 6 if you multiply those 2 matrices together and then do that transformation. You better get 6 as the determinant. But you can also get 6 by just saying, well, I'm going to double and then I'm going to triple. So that's the argument there. What about, is the determinant of A times B the same as the determinant of B times A? A times B isn't always B times A. So is the determinant of A times B the same as the determinant of B times A? Okay, a couple people said yes, some people are nodding their head. Why? So determinants are numbers. These are just constants, right? So here I can change the order because I'm just multiplying 2 constants and then apply this property back and get B times A. So even though the exact transformation won't be the same, doing A times B and B times A, the amount that they would change the volume or area would be the same. If A is a matrix, if A be a matrix, sorry about my English, then if you take the determinant of A to the nth power, then that's the same as taking the determinant of A and then raising that single value to the nth power. And that's just applying the product property multiple times. Because you could rewrite A to the nth as A times A times A times A times A. Take the determinant of that, and that's the determinant of A times the determinant of A times the determinant of A, et cetera, n times. We already talked about the inverse of the matrix. The determinant of an inverse matrix is 1 over the determinant of the original matrix. Determinant of a diagonal matrix or triangular matrix is a product of the element of the principal diagonal. You multiply those entries. We've already done that. And the last one, the determinant of A is the determinant of A transpose. This one's harder to give, like, you can't just give an intuitive reason for this one. I tried last time, I think, by talking about, well, you can expand along any row or column, and you could choose all the way down to pick your rows on one, make the columns of the other one. That could be one argument. But we're going to do a proof here of this, and we're going to use the product property and the product property of transposes to prove this. And so doing it, it'll help us better understand why this is true. So start up, there's 2 cases. So I'm going to first assume A is not invertible, and then we'll do another one for if A is invertible. This is the easy case if A is not invertible. Because if A isn't invertible, then the determinant is 0. But if A is not invertible, what do we know about A transpose? Not invertible. So the determinant of A transpose is 0. We know this one by the invertible matrix theorem. So, and so they're both 0, so they're the same. Easy. I wish the second half was this easy. Not so easy. So we could assume A is invertible. So now I'm going to use a fact from the invertible matrix theorem about something I know about A. If A is invertible, it is a product of elementary matrices. And so I wrote down the product of all those elementary matrices. So now I'm going to look at A transpose. A transpose, I'm going to transpose this side and this side. I have to use a property of transposes to write it like this. What's different about this and this? Some of you missed points on the last exam because you solved an equation and you didn't apply this property correctly. So what has to happen here to here? Yeah, we have to change the order of the products. Here we went A1 to AK. Here you have to go AK down, and you take the transposes. Okay. And so then I take the determinant of both sides, and so now I have the determinant of A transpose. I'm going to work on this other side until I get down to the determinant of A. So the determinant of an elementary matrix, the transpose of the elementary matrices, I can use the product rule, the product property of determinants to write it down as a bunch of determinants. And what I would like to do is I would love to be able to just go from the determinant of E to the K transpose and say, well, that's the same as the determinant of E to the K. Wouldn't I like to do that? I would like to do that. I'm going to put a big question mark right here. I would like to do that because then these are just numbers. I can rearrange them to go E1, E2, E3, et cetera. Use the product property of determinants to write it like this, and I just get the determinant of E1 up to EK, that product, and that's the same as A. But this is the big jump. And I can't just, I have to be really careful here because I'm trying to prove exactly what I'd like to use. So I have the determinant of an elementary, the transpose of an elementary matrix is the same as the determinant of a matrix. I mean, if I knew this was true, then I could just apply it, but then we're doing circular reasoning. But it has helped me a little bit to get to here, because here I'm not trying to use any general matrix. I only have to think about elementary matrices. And if I can show that the determinant of the transpose of an elementary matrix is the same as the determinant of the elementary matrix, then I can jump to there, because that's all. Then I can just apply that to each one of those. Well, we only have 3 cases for elementary matrices, so let's look at each one of these. An elementary matrix, just to remind you, we take the identity matrix and we do one of the 3 row operations. So these aren't proofs for each of these cases. These are just trying to convince you that they're true. So if I take the identity matrix and I multiply one row by a non-zero constant, and I take the transpose and then I take the identity, is that going to be the same as, well, that's the same as just this. Why? Yeah, it's a symmetric matrix, so the transpose is itself. So the determinant, I erased K over there for some reason. So here, since this is symmetric, I take the transpose, I get itself, and so I can take, if this was the elementary operation, then I can take the transpose off. So the determinant of the elementary matrix in this case, transpose is the same as just the determinant of the elementary matrix, and it's K both times. Like the determinant of these is whatever I multiplied that one row by. Okay, are we good on this one? Okay. How about if I swap two rows? Swapping two rows or columns, or I just took a 3 by 3 and I swapped, and I took the transpose, and I got itself. But is that always going to happen? Is it always going to happen if I swap two rows that I'm going to end up with a symmetric matrix? Some of you are going like this. This is where I wasn't sure. This is where I sat down to prove it to myself to make sure I convinced. So this is, proofs get, I know Mr. Proof gets bagged on by students a lot, I know. But proofs are how we learn, how do we figure stuff out in mathematics, how we know things in mathematics. Other fields have different ways to do that, right? You gather data and you analyze data. Mathematics actually isn't the only field that uses proofs. Statistics, computer science, physics, philosophy, they all do proofs also, as keep it in there as a tool in their toolbox of learning. But I had to sit and convince myself out by doing the proof. So when you, we won't go through the proof now, but yeah, when you swap two, you do end up with a symmetric matrix. So if you pick your rows, then you can do the proof by thinking about which rows you're doing and where the columns are that you're swapping, and your i's and your j's and your j's and your i's will be swapped. So they'll be symmetric. And we know that if we swap two rows of columns from the identity matrix, we get just a -1 for the determinant. So the transpose of swapping two rows and columns of the identity matrix, that elementary matrix, it's the same as just getting the determinant without the transpose. Case 3, what if we add a multiple of one row to another row? Doesn't change it at all. Why not, Ian? Yeah, the matrix, it's still a triangular matrix. You have to convince yourself that no matter what you multiply a row by, and no matter which other row you add it to, you cannot change the diagonals. They will all stay 1. And it'll always stay a triangular matrix. So when you transpose it, you still have a triangular matrix. The diagonal entries are all the same. So you multiply them down, it's still 1. So it works. We just proved for, as long as they're elementary matrices, we know these all work. So now we can confidently take off that question mark, and we can take off the transposes, and we know those will be the same. Now I can reorder them, apply the product property, so I get the determinant of E1 up to EK, and that's the same as the determinant of A. So, Ian.
Earlier, when the person on Zoom asked the question about why we can use columns, he said that because it's a transpose matrix, right? So how come we're able to do it right there when we're proving that?
Yeah. So this, I could say, we could stick with just row operations for here, and then we could prove it for row operations, and because the elementary matrices were actually technically just defined for row operations. So maybe I should take that column off. But then I know, but then once I know that, oh, it's the determinant of A is determinant of A transpose, I could transpose that, do row operations on the what were then the old columns, and I know it's going to be the same. Nice, nice job. Okay, any other questions or comments? Okay. So word of advice, it's easy when you have long lists of properties like this to sit down and just try to memorize them all. I would try to convince yourself, try to think about and convince yourself why they're true. So you have a way of thinking about that. And then usually you can more easily remember them, and maybe you don't even have to like memorize them because you'll already understand what properties things have. So maybe it took me a little while to learn, but I hardly sit down and try to memorize things in math class. I try to just make sense of why, when I first learned, I try to make sense of what's going on and why that's true. And then I can just reproduce it if I need. So, and in the long run, it's a lot better. Especially you can use them for problem solving a lot better. So, yes, Ryan.
I don't really get number 6 because the way you did it in the problem here, because it says that if you multiply all the elements of the row by a scalar, then the new determinant is going to be that scalar times the old one, right?
That scalar times the what?
Like the given.
Yes.
So why is it that when you multiply like the second row there by a third, the whole thing was multiplied by a third?
It was. So so the question for those online, he had a question about number 6, the one that's number 6 right now. It seems like we're doing the wrong thing here. So this, I went from there to here. We multiplied that second row by a third to make this 1. We wanted this 3 to be a 1, right? So I multiplied by 1/3. It did change this. So if I didn't have that 3 here, this would be 1/3 as much as this. But I don't want them to be 1/3. I want them to be the same. So then I have to multiply this by 3 to keep them the same. So, okay, good. Okay, other questions? All right. I'm going to throw up a simple 2x2 system of equations for you. You're free to find the solution. I mean, like, go ahead and solve this. I'll write it up over there so you guys can see it. Sorry about that. Yeah. If I can get to a board here. You're welcome. You might not thank me after you see the problem, but. Solving. What else do you do in math class? Suffer? Oh, come on. If you think my class is suffering, man. But the class I had my Calc 2 that I had Calc 2 from, he was a professor. My dad actually had calculus from him also many years before. Awesome guy, great guy. But I heard one of the other math professors describe him as, he likes to teach all of mathematics in every class that he teaches. And it was so stinking hard. I'm just so hard. He'd give open, it was open book, open neighbor, open math lab TA tests. And we still could like hardly do the problems. Like you still couldn't get 100% on those things. Oh, it was so hard. And he made us take 2 finals. It was the very first semester where there was a departmental final. Like the department was writing the final. You guys all faced that here if you took calculus here. But he wanted to give his own final too. So we had to go take the department one, and then we had to go take his final. Oh, so hard. I ended up getting like a 69 or a 67 on that departmental final, and I should have got in the 60s on his. His was 15 problems, multiple choice. I understood 10 of the questions. There were 5 questions I didn't even understand what he was asking. And so, about 2/3. And I got 9 of the 10 right. The ones that I understood the question, I got 9 of the 10 right. The other 5, I was just guessing. Kind of do the best I could at looking at they were multiple choice. I'm like, I don't think it's those, kind of narrow it down. I ended up getting 4 of the 5 right. And just it bumped me way up in the curve, and I ended up with an A- when I should have deserved a C. So, yeah, I definitely did not have A- understanding of the material for sure. So, how's this going? Okay. So, you guys are free to stop. Does anyone have the solution yet? Okay. So it would be really nice to have a formula for X and Y that you didn't have to do the row reduction of, and you could just plug in the numbers and calculate X and Y. There is one. It's called Cramer's rule, and it uses determinants. The thing is, it's pretty much only useful at the 2x2 level. And in practice, even then, you're probably now just going to use, type it into Wolfram Alpha or something. It's not very, once you get to 3x3 or higher, it's just takes a lot of work. Now you can have computers do it for you. But let me explain how to find X. I'm going to take the coefficient matrix, find the determinant. That's going to be the denominator. And I'm going to take, I'm going to take my constants over here and put them in the X column. So that's going to be 0.1, 15, keep this other one the same. Now I get 15 minus a negative, so it's going to be positive 7 times 17. 7 times 10 is 70, 7 times 7 is 49, so it's 119. Here I get 0.1 times 5, which is 0.5, plus minus a negative, which will be plus 7 times 15, which is 105. So X is 105.5 over 134. Pretty fast. That's for X. We still have to do Y. But Y, you do the same thing. The denominator is going to be the same. The denominator is 134. But now in the numerator, I take my constants and I put them in the Y column. So 0.1, 15, and keep my 3, 17. And what do I get? 45 minus 1.7 over 134. So you get 43.3 over 134. A lot faster than that crazy thing going by hand. A lot fewer calculations, and we avoided a lot of fractions. We end up with a fraction at the end, but if they were all whole numbers to begin with, you just end up with whole number operations, and then you have the fraction at the end. So I can give you almost anything right now. 7x minus 20y equals a half. 13x plus 2y equals 5. You can almost just write down what x and y equal. Well, the determinant of the coefficient matrix is going to be 14 minus a negative 260, so 274. That's going to be that's the determinant of the coefficient matrix. 274. And so to solve for x, I take that, put it over here. So I'm going to have a half times 5. So it's going to be 5 halves minus, and I'm going to have, oh, sorry, I made a mistake. Put it over here. That's a half times 2. Right, I'm going to take this column, put it where my x's are. I'm going to have a half times 2. So it's going to be 1 minus, I'm going to have 5 times a negative 20. So it's plus 100. So 101 over 274. That's what x is. And y, so y I put right here. So I'm going to have 7 times 5, which is 35, minus 13 halves. So it's going to be 70 halves minus 13. 70 minus 10 is 60, minus another 3, 57 halves over 274. So 57 over whatever that is doubled. 250 will be 500. Plus 74 will be 48, so 548, if I did that right. So, boom. What have you been doing? You've been learning how to row reduce, and that's good because row reducing has helped us out a lot, finding out whether things are linear combinations of others, and building up, finding spans of null spaces and row spaces and other things. We're still going to use that, right? And this, this is Kramer's rule. Did I tell you that? You don't have to know this for the exam. It's one thing they cut out when we went from 3 credits for linear algebra down to 2 credits. So you don't have to know it. You're not going to be tested on it. I find it useful for 2x2s. That aren't really, where sometimes you can just start row reducing to figure out what y is really fast, and sometimes you can't, and so do Kramer's rule. So, but it really only works for crazy 2x2s. 3x3, the principle's the same. If I have a 3x3 system, that's right. So I could set up an augmented system. So instead of not gonna write my x, y's, and z's. Right, but 1, 2, 3, maybe we'll throw in a negative. I can write down what x equals. So x is going to be the coefficient matrix 2, 1, 5, 3, 0, 1, a minus 3, 1, 0, and 2, and then I'm going to replace this 1, 2, 3, 1, 2, 1, negative 2, 3. A negative 2, 3. There. And then 1, 0, 1, 5, 1, 0. So yeah, I can write this down. That's what x equals, but then I have to find 2 3x3 determinants. At least the other ones, I don't have to find this bottom one anymore, but there's 4 3x3 determinants I have to find. By then, I can probably do the few RO operations, back substitute, or do whatever. So, so mathematicians will use it in proofs, right? They know how they can write down what x equals. They might use it in their theory, but in practice, it turns out not to be very, very useful. Yeah, we can program the computers for the crazy stuff. So, sorry, what? They don't use, oh, so you're thinking, well, maybe you could, if determinants are hard to find and it's easier to find solutions, this connects a solution with the determinant. So are you thinking, could you work backwards? To find the determinants? So they don't usually use determinants just because it's so computationally excessive. They do the row operation thing that I believe. So it's not my specialty though. Oh. Do you want to say that louder?
I don't know if we covered that in this class. It's in some courses. It's something called like LU factorization or QR factorization. And it's just like an efficient way to solve the system.
Yeah. So for those of you online, Porter just talked about that they use a kind of factorization to solve systems of equations, like QR factorization. We will get to a kind of factorization that's really important in what's our next section, 4.3? I think 4.4 is where we do, we'll call it diagonalization. What's another name for that kind of, like the B inverse? I don't know. Anyway, we'll learn how to factor down using eigenvalues and eigenvectors. That makes things a lot easier. That's what I tried to do in this class the other day, where I kind of ruined it with the fox, finding the 15th generation of the foxes and the rabbits, and I failed. So I'll be better prepared next time. There was a hand. So is there a hand? Okay, there was an itch. Okay, all right. So there are formulas that you can just write down for x, y's, and z's, or whatever. In practice, they're not very useful. Similarly, there is something called the adjoint matrix, and it gives you a formula for the inverse of a matrix. And it uses cofactors, and it uses determinants. But again, it's much more computationally intensive than you just doing your process of going through and augmenting it with the identity matrix and going and doing all the row operations, and you'll get the identity on the other side. So it's a theoretical tool for mathematicians, but in practice, it doesn't work very well. Okay, have a great day. See you guys next week. I'm not going to tell you guys the answer to the riddle. If you have an answer, you can come up and test it with me. So one reason is because this a math teacher told this to me when I was a student here at BYU, and it took me a month to figure it out. Not that I was thinking about it all the time, but I just started thinking about it while I was driving somewhere, and as soon as I started thinking about it a month later, the answer came to me. So, but I'm sure a couple of you have already figured it out. That's what happened in the first class. So if you really want to know, you can come up and I'll tell you, but I'd think about it for a while.